Hello, welcome back. So we were looking at the selection rules of fundamental transitions, right? So we'll start from there today again. So for fundamental transition, so we explained in the last class uh, what is a fundamental transition. We'll again recap that. So if I have uh, n number of normal modes for a given particular molecule, and out of initially the ground state means that all of the normal modes will be staying at vibrational level 0. Okay, so which is written as say the product of all the wave functions. Okay, now if I say this is my quantum number, vibrational quantum number, then if n equals to 0, then if all of the wave functions are at 0th vibrational level, then this is my molecular ground state. And if one of the normal modes is excited to the level 1, then I have a situation where I have suppose this is the jth normal mode. So jth normal mode is now staying or residing at vibrational level 1, and rest of the normal modes, which is their number will be now I minus 1, will still stay in the level 0. So this transition is a fundamental transition. So fine. So we want to study fundamental transition because that is the most intense one compared to any other possible transition that we mentioned, like overtone or combination bands, combination transition. Now we got ultimately the rules in terms of the transition moment integral. So when we were looking at the infrared spectroscopic transition, we got the transition moment integrals as one as integration psi Vj. We use this particular terminology. Okay, instead of using this terminology, we use this one. Okay, V is for vibration. Okay, and J is the particular normal mode, jth normal mode, which is being excited. And you have either x or y or z. So this was one, and second was a similar integral with y as the operator, and third one was integration for z. And we said that since this one, this psi v sorry this psi v I is my ground state, and we already said in the last class that the ground state of any in normal mode, in the ground state, will always form the basis for totally symmetric irreducible representation. So this one I don't have to care about. So I have to only care about this part. Okay. So the normal mode that is being excited and the operator. Okay. So if I know the irreducible representation for which this x forms the basis of, then all I need to know what is the irreducible representation for which this normal mode that is being excited forms the basis of. And as per the rule of transition moment integral, whether that will be 0 or non-zero, will depend on whether this overall integral is forms the basis of totally symmetric irreducible representation or contain the total symmetric irreducible representation. So, when we represent this particular product by a direct product of the respective irreducible representation, so that will mean that I need to know the particular irreducible representation of this normal mode. Okay. So, the moment this and this belong to the same irreducible representation, I have a non-zero value for this integral. So, this 3 altogether will give me the selection rule for a fundamental transition in infrared spectroscopy. So, a normal mode will be infrared active if this belongs to the irreducible representation for which either one or more of the Cartesian coordinates, that is x, y or z, okay, form the basis of. So, this is for IR activity. Okay. So, the particular normal modes which will lead to non-zero value, we will say they are IR active normal modes. Okay. On the other side, for Raman spectroscopy, we got an integral which is psi Vj P, where P is the polarizability tensor component, right. So, just like here, we can look at the symmetry properties of the polarizability component, which are like this binary products x y or x z or y z, or the squares like x square or y square, z square, or any of the combinations, say like x square minus y square and so on. So, this kind of functions will form the polarizability tensor. They represent the polarizability tensor component. So, I need to know the symmetry of those x y or y z, x square or y square and so on, and the normal mode that is being excited, okay, that should form the basis of the same irreducible representation for which the particular polarizability component form the basis of. So, suppose I have a component x y, suppose which forms a basis for say AU, then my selection rule says that this transition will be allowed only when psi v j also form the basis for AU, right, because the direct product of AU to AUs will give me the totally symmetric irreducible representation, and then my integral will survive. So, here what is the selection rule for Raman spectroscopy? Selection rule for fundamental transition, that will be Raman active, that is that particular normal mode of vibration will be Raman active when the normal mode belongs to the same irreducible representation to which this binary combinations, that is x y, x z, etc., will form the basis for. All right. So, after getting this thing, we are in a position to talk about the that which particular modes, which particular normal modes that we deduced, say for CO3 2 minus or say N2F2. So, which one of them will be IR active, which one of them will be infrared active, right. So, say for CO3 2 minus, we got the normal modes which are genuine, which represent genuine vibration. they were A1 prime, A2 prime, I think A2 prime or A2 double prime, and 2 E primes. Now, if you consult the character table, you will see that among these A1 prime, that has this Cartesian coordinate component, okay, as its basis. Okay. So, this one will be infrared active, while this one has this binary function as its basis. So, this one will be Raman active, right, and this E prime, it has both the only Cartesian coordinate as its basis as well as the combination of Cartesian, binary combination of this Cartesian coordinates. So, this will be IR active as well as Raman active, right. Okay. So, we also had this N2F2 molecule, for which we had this vibrational modes like 3 Ag plus Au plus 2 Bu, right. Now, if I look at the character table of C2H, so what I see that Ag has this only the binary functions like x square or y square, z square, xy. Okay. So, these binary functions tells me that Ag will be a Raman active mode, while this Au, it has z as its basis and Bu has x or y as its basis. So, x, y and z, they transform as either Au or Bu. So, this Au and Bu, the modes which transform as Au and Bu will be infrared active, correct. So, these two will be infrared active normal mode, while this 3 Ag will constitute Raman active normal mode. Now, one thing you notice here in this particular molecule CO3 2 minus, I have one mode which is IR active but Raman inactive, another mode I have Raman active but IR inactive, and we have certain modes which are both IR active as well as Raman active. Okay. So, when you look at N2F2, I see that none of the modes are Raman as well as IR active. So, those modes which are IR active are not Raman active and vice versa. So, there is a difference between these two. We will talk about this one. We will take another example, another particular molecule, for example like ammonia, and look at the particular example and see what happens there. Okay. Then we will come to some conclusion about this or the reason behind this kind of observation. Okay. So, now after we could separate out the Raman active or infrared active modes using the symmetry. Now, we will go back to the original problem of this N2F2 molecule and its normal modes. Okay. So, we got this this 6 normal modes and their symmetries. Now we do not have any idea what are these normal modes, okay, how do they look like, okay. So how do we do that? So here at this point we will take help from so called internal coordinates, okay. So what are internal coordinates? We mentioned it earlier, let me tell you again. So this internal coordinate will be either the bond distance or a bond angle, okay. So in case of N to F2 I have this is the structure. So how many bond distances I can take? I can have NF, 2 NF bond distance and 1 NN bond distance, okay. So I have 2 NF, I have 1 NN, then I have this angle as well as this angle. So I have both of them are same. So I have N F angle, right. So there is no hard and fast rule that okay which one I will use as my coordinate and which one I will use first, which one will I use later. So it depends on what you want to do. Now since we are dealing with a vibration, which means either the bond distance will alter or the bond angle, the amplitude will alter in plane or out of plane, okay. So let's start with this. Now before even starting with this internal coordinate, what we will do, we will have a look at the character table once again. So if I look at the character table here for C2H, what do we have? So if we look at the we have 3 different types of irreducible representation, according to which the normal modes get transformed. So out of this 3 AG, AU and BU, I have this AU, particularly this one, this has a character of -1 for, so sigma H equals to -1, okay, while for AG and BU the character for sigma H is +1. So what does that mean? That in this AU mode the bond displacements or bond angle change is such that the structure is not symmetric with respect to the sigma H plane, rather it is anti-symmetric. So what does that mean? That there is some part of the structures above the plane or below the plane, okay. So that means the particular normal mode which transforms according to AU has some motion which goes out of this plane. Now we started with a planar molecule, right, and now I have a situation where I see that sigma H produces -1 as the character. That means that these bonds, one of these bond is upward, one of the bond is downward, meaning that this motion of this bonds, they are not in plane, rather they are out of plane. So they are doing some kind of out of plane motion, right. So I can safely, to start with, I can ascribe this one as out of plane bending. Why bending? Because this bond stretching, if it goes on in the same direction, it will still remain planar. But in this particular case of AU type of irreducible representation, I can clearly see that will be out of the plane. So therefore the angle, say if I say this this angle here which was in a plane, so after this movement of this F out of the plane, there is a creation of an angle here, okay. So without worrying about anything, I can say that this is a bending motion, okay, because from planarity I have AU, I say this is out of plane bending. So it is like, this one is plus and this one is minus. Okay. So in that way, or it can be in this direction. Now we are left with 5 others. So AG, 3 AG and 2 BU. And if we use this as my internal coordinate, then I am fine, because I am using 5 internal coordinates, and I am going to find out about the properties of the normal modes of 5 such normal modes, right, belonging to 3 AG and 2 BU IRs. Well, so let us do that. Now, here we will use these 2 NF bonds together, right, and so let us look at the representation. So I have this, and then I can have 3 different representation based on NF, NN, or let us say NNF, which is an angle, and then I have the representation based on N double bond, N distance, all right. So E will not do anything, so my 2 basis functions will give me a character of 2. So if I do C2 here, this NF together, they are getting interchange. So I get nothing here. Same is true for I, and sigma h I get 2. Now if I look at the angle, it has the same fate. Okay, these the 2 angles that I am getting. So now when I have this NN bond distance, then identity, of course, it gives 1, and C2 and I sigma h, all of them will contribute 1 to the diagonal. So I get this as my representation. So this one I do not have to do anything, I immediately see this is all symmetric with respect to all the symmetry operations. Therefore, the representation that I am having, this belongs to totally symmetric irreducible representation. So this was very easy, all right. Now I have to reduce this to, okay, and whatever I the result I get for gamma NF will be same as gamma NNF, correct, because they are sorry, this one is 2, they are identical. And if you reduce this one, then what you will see that this one is equal to AG plus BU, and obviously this one will also be AG plus PU, all right. Okay, so I got back my original result that I got earlier using the 3n Cartesian coordinate system. That's good. That says that I have chosen the right internal coordinates. Now why did I do all these things? I have already got this one, so what was the need for getting this one? This is because I need to have some idea about that particular motion of the normal modes, right. So now I get this AG and BU based on this NF bond. That means the normal mode which transforms as AG and BU, they will have some motion of this bond distance, okay, NF bond distance. Now if you look at the characters of AG and BU, let us have a look at the respective characters. So AG is totally symmetric, correct. So then I can safely say that AG is my symmetric stretching mode. Why? Because it is concerned with the NF bond distance. So NF bond will increase in both the direction in equal manner. If it has to contract, both of them will contract in the same manner, and then only it will belong to AG representation. Okay? So, this particular mode is obviously the symmetric stretching mode. So, this is symmetric stretching, and if of course belongs to AG. All right. While if I look at the BU representation, then I see that with respect to I or with respect to C2, this is asymmetric. So, what does that mean? Here, since this is based on this NF bond distance, again it has to do something with the change in the bond distance, and it says that if I operate C2 what it will do, it will take this guy over here and this guy will here. So, this NF bonds, they will get interchanged, and that will give me -1 as my character for the overall molecular structure. That means the change in the bond distance due to the normal mode of vibration, which transforms as this BU, will change two NF bonds in different ways, meaning it will be something like this. So, one will increase, right, while the other one will decrease. So, it is like I have say N2, say like this. Okay. So, this is my NN bond and this is F2. So, this bond is increasing while this is shrinking, and then when this one is shrinking, then this one is increasing. So, this is asymmetric stretching. So, this BU gives me an asymmetric stretching, which is shown here. All right. So, that was obtained from the representation that we got using NF bond distance. Now, if I look at the representation that I got out of NNF, all right. So, NNF is an angle. So, whatever the normal modes that I am talking about has to do something with the change of these angles. Okay. So, AG is a totally symmetric IR. So, the normal mode which transforms according to this AG must change these bond angles in a very symmetric way. That means, if this bond goes here, making this angle shorter, then this will also go in this direction, making this one similarly shorter. So, this will be a symmetric bending mode. So, if I can write here in what it will happen. So, okay. So, both of them will move in opposite direction by equal amount, so that this angle is changed by the same amount. Okay. So, this is the symmetric bending. Okay. So, this is symmetric bending and it corresponds to BU. Sorry, this will be corresponding to AG. I am talking about this particular AG. Okay. Now, what will be the BU? BU will also be a bending mode, because it deals with this angle, and in this case, if I look at the character table of the BU, like before, it has a it has asymmetry with respect to C2 or I. So, there it should be asymmetric kind of movement, right. So, therefore, it will be asymmetric bending. So, if I have F here, then if this angle becomes shorter, then this will become larger. So, if this goes in this direction, this also goes in this direction, or vice versa. Okay. So, this is asymmetric bending motion and has a symmetry of BU. All right. So, we are left with this last normal mode having AG symmetry, and this was born out of this NN bond distance. It's totally symmetric. So, this NN bond distance either increasing or decreasing. Okay, it's purely symmetric, right? You can say. So, like, you know, if you talk about this one, so they will go apart and they will, you know, come closer. So, in a very symmetric way. So, overall that will be a completely symmetric with respect to all the symmetry operations. So, this one will be the NN symmetric stretch. Okay. So, that will be symmetric stretch. Fine. So, see now if you look at all the symmetry, you know, all the normal modes, and you know, when you look at this presentation of these normal modes, it is absolutely clear, right? So, to start with, we did not have any idea like what are those normal modes, how will they look like, because if I, you know, give you the molecular structure and ask you to draw the normal mode structure, you may not be able to draw exactly what is, you know, what we obtained just now. But if you go in this way, you exactly know, okay, I have used this as my basis set. So, whatever change is happening on this particular bond or on this particular angle or this particular bond. So, looking at the symmetry, okay, of that particular representation that we got using those basis functions, I can unequivocally comment on this particular normal modes. So, this is how we get the character of the normal modes knowing their symmetry properties. All right. Now, before we stop today, we will mention one more thing. Suppose I take another molecule, okay, say ammonia, and take all 3 n coordinates and form the representation. So, for ammonia belonging to C3V point group, I have E, C3 and sigma V, correct. So, if I form gamma 3n, we have 12 for E, C3 will yield nothing and sigma V will do 2. So, you can verify yourself this one, and once you reduce it, you will get you know, the total all the irreducible representation contained in this representation, which will be 3A1 plus A2 plus 4E, all right. And out of these representations, what you will get is for normal vibration, you get 2A1 plus 2E. Fine. Now, if you try to find out which one of these normal modes will be infrared active and Raman active, you will see both of these will be IR as well as Raman active. Now, let us compare the 3 compounds that we looked at, one belonging to D3H symmetry, another belonging to C2H symmetry, and this third one that we just looked at is C3V symmetry. Now, D3H had a thing like certain normal modes will be infrared active only, certain normal modes will be Raman active only, and certain normal modes will be both Raman as well as infrared active. In case of C3V, I have all the normal modes are simultaneously Raman active as well as infrared active. In case of that molecule N2F2, which belongs to C2H point group and is centrosymmetric, I get those particular normal modes which are Raman active are not infrared and vice versa, meaning that for that particular molecule and the particular point group, the Raman active modes and infrared active modes are mutually exclusive. Okay, so this is a special character of molecules which are centrosymmetric in nature. Okay, so we will stop here today and we will elaborate this issue in the next class. Thank you very much for your attention.